Okay, there is a very easy theorem to show that every terminating decimal is a rational number, and I'm going to not prove this but show by example. And this example should make it really obvious really quickly that this is true. As an example, let's do 3.25. And hopefully all of you know that this would be read as 3 and 25 hundredths, or you could even read it as 325 hundredths. And just even from that example, hopefully you can see that we did manage to write the terminating decimal as a quotient of integers. As another example of this, let's just do something like 0.475. We can write this as 475 thousandths, the same way you would read it as 475 thousandths. And notice once again, we managed to write it as a rational number. Now, I could actually reduce these, but it doesn't change effect. We have already shown that we can write them as a quotient of integers. Reducing doesn't really do anything for trying to explain that this theorem is true. Now, there is a theorem which states that every repeating decimal is actually a rational number. Now, I'm not going to prove this, but I'm going to give you an example which should make it really obvious that it's true. As an example, let's just make up a repeating decimal. Let's do 3, 7, I don't know, let's say 5, 8, 5, 8, 5, 8. Notice the 5 eighths are repeating, and they repeat forever. And as most of you know, this can be rewritten as 0.37 and then 5, 8 with a bar. The bar shows the 5 and the 8 keep repeating forever. Now, the way I'm going to actually show that this can be written as a quotient of integers is to name this x. And notice two spots repeat. And if I multiply by 100, everything will shift by those two spots. So 100x is actually 37 point. Notice the decimal shifted. And then we have 5, 8, 5, 8, 5, 8, 5, 8. And again, forever. And again, 1x was just 0.37, 5, 8, 5, 8, 5, 8, and so on. What I'm going to do here now is to actually subtract these. Now, if we subtract these, notice all of these 5 eighths cancel, and it cancels forever to the right, and all that leaves is the hundredth spot and to the left. So we have 8 minus 7 is a 1. 5 minus 3 is a 2, though notice it's actually 21 hundredths, and then we also have 37. And on the left side we have 100x take away 1x, which is 99x, and now we can get x by dividing by 99 and get 37.21 divided by 99. At this point we still don't have a rational number because the top and bottom both need to be integers. 37.21 at this point is not an integer, but if we multiply the top and bottom by 100, it doesn't change the value of the fraction, but now the top is 3,721, which is an integer, and the bottom is 9,900, which is also an integer. And just to show you that this actually works out, let's take a calculator. And we're actually going to do then 3721 divided by 9900, and notice it is 0.37585858. Now the reason it says 59, it was a 58, but the digit to the right of that 8 is a 5, and so it rounds up to a 9. So as you can see, we were able to write a repeating decimal as a rational number, and it should be reasonably obvious that this is possible in every case where this happens using this method.